Okay, this is quiz 3 for 21C. The first question reads, do the following sequences converge absolutely, converge conditionally, or diverge? You must thoroughly explain the test that you are using. Okay, the first problem we have is the series that runs from n equals 1 to infinity of negative 1 to the n over n plus the cube root of n. Okay, notice this is an alternating series. Negative 1 to the n is going to push that back and forth between positive and negative. So we know right away that we need to apply the alternating series test. Now, the alternating series test has three requirements. First, that this is going to be u sub n. And the first thing we need to know is that the u sub n's, which is 1 over n plus the cube root of n, is greater than or equal to 0 for all n. The second thing we need to know is that eventually it's non-decreasing. So eventually, if we go far enough out, u sub n plus 1 is, less than or equal to u sub n. Now this is actually true for all n in our case, so we're always fine. Okay, and then finally we need to know that the limit as n goes to infinity of u sub n is equal to 0. And that is all true for this 1 over n plus the cube root of n. So that tells us the series converges. Now, we don't yet know if it converges conditionally or absolutely. We know it's at least going to converge conditionally, right? So now we just need to check if it converges absolutely. If it does not converge absolutely, then we know that it converges conditionally. Okay, now we can check to see that it does not converge absolutely using either the limit comparison test or the comparison test. So with the limit comparison test, the limit as n goes to infinity of 1 over, now notice the absolute value of this, of the terms in the series are just going to be 1 over n plus the cube root of n, right? That just gets rid of the negative 1 to the n. So the limit of 1 over n plus the cube root of n over 1 over n is the limit as n goes to infinity of n plus the cube root of n, is n over n plus cube root of n, which is 1. So by the limit comparison test, we know that these two series share the same fate. So our absolute the absolute value of our series diverges, since the harmonic series, which is what we compared with, diverges. Okay, so I'm also going to show that we can use the comparison test to do this same process. So by the comparison test, we know that 1 over n plus the cube root of n is greater than or equal to 1 over 2n for n greater than or equal to 1. So that tells us that our series, the absolute value of negative 1 to the n over n plus cube root of n, is greater than or equal to the series 1 over 2n, which diverges because it's some multiple of the harmonic series. Okay, so that so those diverge. So that tells us, since we know that the alternating series converges, but the absolute value of the alternating series diverges, we know that this series converges conditionally. Okay. This next problem says the series that runs from n equals 1 to infinity of negative 1 to the n cosine of n pi over n plus cube root of n. Now the first thing to notice is that cosine of n pi is actually just going to also alternate. So for example, cosine of 1 pi is -1, cosine of 2 pi is 1. That will always alternate. If we look at our circle, every time we go around pi, we're at -1, then 1, then -1, 1. So this is just going to be also -1 to the n. So we have -1 to the n from the original alternating part, and then another -1 to the n from our cosine of n pi, and that's all over n plus the cube root of n. Well, this is, you can see when we have a -1, so when n is odd, these are going to cancel, and when n are even, these are going to cancel, and we're always just going to have 1 over n plus the cube root of n. Now, we showed before, using both the limit comparison test and the comparison test, that this series 1 over n plus the cube root of n diverges. So this diverges, strictly diverges. Okay. Now this last problem, number 2, says find the interval of convergence for the following power series. Give your answer as an interval. The series is n equals 1 to infinity of the quantity x minus 3 to the n all over n. Okay, now we should start out, we can either use the ratio test or the root test. Here the root test works really nicely, so let's do the root test. So the limit as n goes to infinity of x minus 3 to the n over n to the 1 over n, that's just going to be equal to, we can do the top and bottom separately. So x minus 3 to the n all to the 1 over n, that's just going to be x minus 3 in absolute value over n to the 1 over n. Now, as n goes to infinity, n to the 1 over n goes to 1. So this is just x minus 3. Okay. Now what we know using the root test is that we need this to be less than 1. Okay, so that tells us that in order for this to converge, we must have x minus 3 is less than 1. Well, the absolute value of x minus 3 is less than 1 is the same as -1 is smaller than x minus 3, which is less than 1. Well, and then if we add 3 to both sides, we get 2 is less than x is less than 4. So initially we know that any of the x values between 2 and 4, not inclusive, will force this to converge. Now we need to check these endpoints. So let's start for x equals 4. The series just ends up being the summation from n equals 1 to infinity. Now 4 minus 3 is 1 to the n is always just 1. So this is 1 over n, which clearly we know the harmonic series diverges. Okay, for x equals 2, this series ends up being, when we put in 2 here, we get -1 to the n all over n. And if you think about it, the alternating series test will show us that this converges because the limit of 1 over n as n goes to infinity is 0. It's always decreasing. And the 1 over n, the terms without the alternating part, are all positive. So this converges by the alternating series test. So that tells us that our entire interval is, we include 2, but we don't include 4. This is our interval of convergence.